Hello everyone, and welcome to the NEATEC Electronics Series. This video is about counters, so let's get started. Hello everyone, and welcome to a video about counters. So first off, I wrote some definitions over here on the left, okay? So I would like to briefly go over these definitions, and I'm going to point these things out when we're working with counters, all right? So the first thing is a counter, and as you think about it, what is a counter? Well, it's something that counts, right? Like 1, 2, 3, 4, 5. So when you think of a counter, what do you have? You have a direction. It's either going to be up or down, right? And you need to have a step size. So in your counter, you can say you're going to count starting at 0. You're going to get the up counter I have here. I'm drawing an up counter, and you're going to count to 5 by ones. All right? That's how we're defining a counter, okay? This information is necessary because you can make a counter that counts by 2s, by 3s. It can go up, it can go down. It doesn't have to start at 0. It can start at any number you wish, okay? Now, suppose you're counting from 0, just like this, up to 5, and then going to recycle. This is a recycle. Okay, that's what we have right here. So basically it's going to restart again at 0. So it's going to start at 0, then 1, 2, 3, 4, 5, and then it's going to recycle back at 0, just over and over and over. Hence, that's what recycle means, okay? The count sequence, well, that's obvious. That's going to be by 1s, by 2s, by 3s. Well, how it progresses through your counts, that's what the count sequence is. Now, let's talk about a modulus. Now, this depends on the number of bits too. Okay, I'm just going to draw 2 bits here, right? So we have 2 bits. We can have 0, 0, 1, 0, 0, 1, and 1, 1. Okay? So let's look at this. Here's the state. This is 1, 2, 3, 4. So we have, this is states. We have 4 states in this counter, okay? So if we were going to count from 0 to 3, right, and recycle back, okay, think about it now. We would have a modulus of 4 because that is the number of states in your counter, okay? That's what a modulus is. It's the number of states it's going to go through before recycling or repeating, right? Remember, this comes back up here and for an up counter, okay? Now, we have something called the maximum modulus, all right? Now, this is important. I want to make sure you understand this because we have two bits here, right? And you can see we have 4 states, right? So the maximum modulus for this 2-bit counter is 4, right? So let's say max modulus, it's going to be, say, mod equals 2 to the n, right? Where n, in this case, is equal to 2. Where n is equal to the number of bits. And the number of bits is 2, so it's going to be 2 to the 2, which is equal to 4. Alright? So that's your maximum modulus. Got it? Now, let's try this. You know what, let's just add another one there. That'd be just as good. Suppose we added a third bit here, right? Now, suppose with this new bit that was just added, let's finish writing the number of states, shall we? So this will be what? 0, 0, 1. Then we'll have 1, 0, 1. And we'll have what? 0, 1, 1. And then we'll have what? 1, 1, 1. And quite simply, this is going to be your 5th state, 6th state, 7th state, and 8th state. Remember, these are not what these numbers are. This is 0. This is just the number of states here, right? Obviously, this counts from 0 through 7, but there are 8 total states, right? So what's the maximum modulus of this counter? Well, it's going to be 2 to the n, where n is the number of bits. That's going to be 2 to the 3rd, which is equal to 8. Alright? That is a full sequence counter, because at the end of it, if you basically repeat or recycle, at that point it's going through every state and it comes back. So now you have a full sequence counter. Now, you don't have to. You can have a truncated sequence counter, right? Suppose you wanted to start your recycle, instead of all the way at 8, you wanted to say to recycle start at 6. Alright, that is a truncated sequence counter, okay? So remember, you have two types here, full sequence or truncated, right? And that's the difference between them, alright? Now, the state diagram and the state table we're going to go over in a minute. Okay, I'll be right back. Alright, everyone. Let's talk about a state diagram. And what I have done here is I have drawn one, as you can see. So, if you look at it, we have basically 12 states, don't we? We start, if I write the state over here, right? I'm sorry, I gotta get the pen mode out here. So if this is your state, we're starting at 0, and then we go to the first state. By the way, a state diagram, you always have an arrow showing you where you're going to go. So obviously we go from state 0 to state 1. So then the next one, it would go to state 2 and to state 3, and you could see it would just continue all the way around here. 5, 6, 7, 8, 9, 10, 11, and from 11 it goes back to 0. What do you think this represents? If you set a clock you were correct, right? Because this is just like a clock, isn't it? We're at 0, which really is 12, right? But we can say it's 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then it starts back again, right? So in a state table, as we were saying here, you have your states. Each circle, I'm going to draw a circle up here. Each circle represents a state, all right? And now, in this case, we have 4 digits in there, 4 bits. So this gives the binary number that corresponds to that state, okay? They don't have to be equal. We could put number 3 in state where state 1 is, and the number binary 1 where state 3 is. All right, so it just so happens is in this instance they're the same. But for this state, whatever that state is, it corresponds to 0, 0, 0, 0, okay? And it's in a circle, and it's going to have an arrow pointing to where the next state is. The next state, going to have a circle. You're going to have 4 bits in there. In this case, for this specific one, because there's 4 bits in each of the circle, right? You don't have to have 4 bits, obviously. It all depends on your diagram, how many states you need. You could have fewer, you could have more. It all depends, all right? And remember, this is very important. Don't forget your arrow, because when you're in this state, when you're clocked, you need to know where to go. So if you go to the next state, all right? Does that make sense what I just said? You need an arrow, because when it receives a clock pulse, it needs to know where to go, and this tells the next sequence of what would be displayed, for example. All right. So this is a state diagram. It really, I think it gives a visual representation of what you're trying to do. When you're thinking of a circuit and you think about where you want it to progress through what states, this is beautiful, because you can literally just look at it and you can go through it in your mind and see what's happening, all right? Now, in a minute after this portion, I'm going to bring up a circuit, and you're going to see a state diagram. You'll see some things in there in the state table. What we're going to do is we're going to go from this circuit I'm going to show you to a series of states. So in other words, we're going to do it backwards, if this makes any sense, all right? So we're giving you the circuit. I'm going to help you through it. And then from that circuit, you're going to determine the count sequence, and you'll determine the number of states in the circuit before it recycles, all right? All right, everyone. See you in a few seconds. All right, everybody, welcome back. So as I stated earlier, I was going to give you a circuit. On this side right here is your circuit, okay? It consists of 3 JK flip-flops and an AND gate, okay? Now over here I wrote the truth table for a JK flip-flop, okay? Actually, I think that's termed the excitation table, but you get the idea. I mean, if JK is 0 and you clock it, NC stands for no change. Reset, that's for Q bar to be high and Q to be low. Set, that's for Q to be high and Q bar to be low. And 1 1 obviously means toggle, and we went over that, all right? Now, since we have 3 of these, I also wanted to tell you something else about a flip-flop, right? I think, I want to say most of them, if not all of them, they have these two extra inputs here. One is going to be called a clear, C-L-R, C-L-E-A-R, depending on the data sheet. And the other one's going to be called a preset, right? Now listen, I drew mine where the clear was on top, the preset was on the bottom. Sometimes they change those. In fact, I honestly think most of the time the preset is on the top and the clear is on the bottom, but it doesn't really matter. The thing is, and they're both here, and I'm not going to put them in because I don't want to clutter up the drawing, okay? But generally, if you attach your clears to your clear inputs to a switch, you can reset the whole counter, right? And you clear it, which means you make Q0, right? Or you have a preset, you can attach those to a switch and you could make them all ones, right? When you preset it, that means Q is going to be 1, okay? Now be aware, many of these inputs have these little inverter bubbles on them. So that means your switch, when you flip your switch, you want to be careful of your polarity. So if in that case, when your polarity goes low, it's expecting an active low, right? That's going to clear it or it's going to preset it. It all depends on the chip you're using. But just be aware of those inputs, okay? But for this specific one, this specific circuit we have here, I drew what is called a state table. And let me just label it right here. There you go. Notice we're starting out down here. I'm just going to put a little dot so you know where I'm focusing on. Each state is 0 to begin with, all right? Now, we have to determine the value of JK, all right, and the equations. So let's do this down here. So since this is 0, we're going to have J0 and K0. What are they going to equal? Well, they're connected to VCC, right? So they're both going to be 1 no matter what. They're not going to be 0 because they're not connected to ground, right? They're always going to be high. So it's a 1, right? Now, let's look at the next one. If we're over here, J1 is going to equal, so let me just write this down for you, J1, K1. What's J1 going to be equal to? Well, J1 is going to equal Q0, isn't it? Because it's attached to it, isn't it? And K1, now we're looking here, I'm going to put a little X here, we're looking at this right here. It's the middle flip-flop. So J1, and since K1 is connected to J1, it's going to equal the same thing, isn't it? So they're both equal to Q0. Now what about J2? Here we go, guys. Right there. J2, well, that looks like it's the output of an AND gate, isn't it? See? It's coming right out of here, right? So what are the inputs to that AND gate? Well, you have a Q1 and a Q0. You see it? Here's your Q1. Here's your Q0. And they're both of those are ANDed together. So it's going to be Q0 ANDed with Q1. And since J2 is connected to K2, it's going to be the same thing, isn't it? Q0 ANDed with Q1. Alright. This is important, this first step, because you have to get your equations right, okay? I'm just going to write them down here for you. Okay, so I'll just put 1 there. That's the first thing you got to do. You have to get your equations right set, all right? Now, once you have your equations set, we can go through and fill in the state table. I'm just going to write a number 2 over here. That's the next thing you do, okay? So now let's start filling out the state table, number 2, okay? So, looking back on the current circuit as it is right now, J0 and K0 are both 1. We got to look at our equations, right? They're both equal to 1. And that's not going to change because they're connected to VCC. So J0 and K0 are both 1. I'm going to put that in there, right? J1 and K1, well, they're both equal to Q0, right? Well, we've said that Q0 is equal to 0, right? So they're both going to be 0 and 0. And 2, J2 and K2, and now we're on this one over here, right? This one right here. That has Q0 and Q1 ANDed together. And since Q0 is equal to 0, actually Q1 is equal to 0, they're both going to be 0, right? Now, the next step, clock it. So if you clock it, Q0 is a 0, right? I'm looking right here. That's going to change and it's going to become a 1. Now, if you notice, because we just had a toggle, we were just in a toggle state there. I don't want to go by that too fast, because 1, 1, as you have right here, J and K are both 1s, Q0 is 0, so if you toggle it, it's going to toggle to a 1, right? The rest of these states here are 0, 0, right? That's up here. That's the no change state, right? So these are both going to stay 0. Got it? Now, the next step is you write down this new state. You bring it all the way over here. That's what you just got, right? Now let's do this. Here you go. Alright everyone, let's do the next one, shall we? After you've written your next state down here, which is 1, 0, 0, right? Let's start filling in the inputs again. So J0, K0, we have to refer to our equations. That's equal to 1, isn't it? So that's going to be a 1, and that's going to be a 1, right? J1 and K1 are both equal to Q0, right? Well, Q0 is equal to 1, isn't it? So that's also going to be a 1, 1. Okay? I don't mean to slant my 1s. I'll make that a little bit straighter for you so you can see it. Okay? Now, J2 is equal, and K2 are both equal to Q0 ANDed with Q1. Well, you can see them right here. You have Q0 and Q1. One's a 0, one's a 1. It's both going to be 0, right? So it's 0, 0. So what's going to happen? Well, if we refer back up here into this excitation table, Q0, right? It's 1, 1. That's going to toggle, isn't it? So it was a 1. It's going to toggle back to a 0. Now in this state, J1, K1, they're 1, 1. So that's also in the toggle state. So Q1 is 0 now. It's going to toggle to a 1, isn't it? Makes sense. And Q0, I'm sorry, J2 and K2 are both 0. So that's no change. That's going to stay right where it is. What's the next step? Let's write it down here. We're going to try this. Come across here. You know something? I did that in blue, didn't I? You know what? Let's go with it. What the heck? We're going to have some variety in our lives, all right? So, let's go through it. What are we going to have here? Well, J0, K0, they're both equal to 1. That's not going to change, right? Now, J1, K1. They're both equal to Q0, aren't they? Well, what's Q0? Q0 is 0, so this is going to be a no change, right? And J2, K2, well, that's Q0 ANDed with Q1. Since Q0 is a 0, no change. They're both going to be 0, right? So in this case, Q0 is going to toggle, which is what you would expect. J1, K1, Q1 is going to stay the same, right? Just bring it right on down. Q2, no change, right? So now let's bring this one down, shall we? You know, folks, I want to tell you, I'm not exactly sure where this is going to end. This is kind of exciting. So let's do the next one over here. This is tedious, but this is how you have to do it. I don't know what else to say. You just got to go through until it starts to repeat, and you'll see that hopefully in a second or two. So what's the next one? J0, K0, well, that's 1, 1, right? There's no change there, is there? J1, K1, well, what's that? That's equal to Q naught, right? Or Q0. Q0 is equal to a 1, isn't it? J2, K2, well, that's equal to Q0 ANDed with Q1. Both Q0 and Q1 are both 1s. If you AND them together, you're going to have a 1, right? Remember, for an AND, both A and B have to be high for the output to be high. So in this case, they're all 1s, which means they're simply all going to toggle. So 1 would toggle to a 0. This 1 would toggle to a 0. This 0 would toggle to a 1, right? What do we do now? Bring it down, write it over again. 1, 0, 0. All right. Now, let's fill this in, shall we? J0, K0. You know that by now. It's a 1, 1. J1, K1, that's both equal to Q naught. Q naught is equal to a 0, so these are going to be 0, 0. And J2, K2, well, since they're both Q0 and Q1 are both equal to 0, you know this is going to both be 0, 0, 0. So what's going to happen here? Well, J0, K0, that means Q naught is going to toggle, right? So that 0 is going to toggle to a 1. Q1, which relates to J1, K1, that's going to stay the same, no change, right? So that's just going to be a 0. And the final one is J2, K2, that's 0, 0, so that's not going to change either. right? So that's going to be a 1. It's just going to come right on down. So let's keep going. 1, 0, 1. You know, I don't want to run out of space. I really hate it when that happens. But if it, yeah, let's just see what happens here, okay? There we go right here. All right, so let's fill this out, shall we? So J0, K0 is going to stay 1, 1 because it's connected to VCC. It's never going to change. J1, K1 is going to equal to Q1, Q naught, or Q1, or Q0, I should say. Q0 is equal to 1, so this will be a 1, 1. Got it? And the next one, Q2, well, it's Q naught ended with Q1. And since 1's a 0, 1's a 1, no change. Okay? So let's see what happens here. Your 1 would toggle to a 0. Okay, that makes sense. The next one would toggle to a 1. And we would have no change on this one, right? Well, we're counting up pretty well. All right, let me do something here because we're kind of running out of space down there below, okay? I'm going to move this table because I want to make sure that you all can see it. I'll put it right there. How's that? That's not bad, right? I'll take this one. Let's move it up. Hey, all right. Looks like we got some more real estate here, doesn't it? So bring this down here, bring this down here. Just freehanding these folks. Sure, when you do these for your homeworks and things, you leave plenty of space because it's a drag when you have to go through and you need like 1 or 2 more rows and you're at the end of your sheet of paper. It's not too much fun, right? But anyway, so let's bring this last one down. We just had one right here, right? We're on this line right here. So let's bring this down over here. So it's going to be 0, 1, 1. That's our present state, right? Now, since that, let me get our line in place here, shall we? Got it. Now, we know J0, K0 is going to be 1, right? Since J1 and K1 are equal to Q naught or Q0, we know Q0 is equal to 0, so that's going to be 0, 0, right? And we know that since Q0 is 0, when you end something with that, Q0 ended with Q1, we know it's going to be 0, so that's going to stay 0, right? So what's going to happen now? This is going to be 1, 1, 1, isn't it? 0 is going to toggle, and the other two are going to stay the same, right? Let me just clear this up a little bit here. All right. Now, let's see what happens. This is getting exciting. Just want to make sure it goes back to 0, right? Because where else is it going to go? It's going to have to go back at some point, right? So now we're at 1, 1, 1. So J0, K0 is equal to 1. You know that, right? J1, K1 is equal to Q0, which is equal to 1, so that's going to be 1, 1. And since Q0 and Q1 are both 1 and they're ANDed together, we know that these are going to be a 1, right? So everything toggles. each one of these toggles to a 0. Look what happened. This line right here, or I should actually draw it here. That's your next state, right? Well, your next state now, if I can draw this right, goes back to the beginning, so it's just going to repeat. Get it? So all this counter does is it counts from 0 to 7 and repeats. I hope this helped you, but going through it once, it puts things in perspective. Just remember, look at your circuit. You got a number 1, come up with your equations. That's very, very important, right? Your equations are vital for everything. And the other thing to remember about this, if you make a mistake in your equation, your table's not going to work out right. So take your time and double check yourself when you're coming out with your equations. Then make your state table. And you notice we had 3 flip-flops here. So we had 1, 2, 3 sets of JK values, JK0, 1, and 2, right? If we had 4 flip-flops, we would have had more sets of inputs, right? And finally, we have your next column. Okay, now listen, depending on different state tables, they may move these columns around, but they're going to keep the next columns together, they'll keep the present columns together, and they'll keep the inputs together. Okay, but you get the idea of what's going on here. So this is important. Make sure you know how to do this, because what this means now is if you're given a circuit, you can analyze it and determine how it's going to count. Okay? Alright everyone, that was quite an exercise. In the next part of this video, we're going to actually design a circuit, a counting circuit. Alright? See you soon.